Welcome back to ECE 441A, 541A. Lab number 1 is due today, and based on the stack that I physically received and the Dropbox size, we still have some labs that are needed to be turned in. That's due today. The Dropbox closes later this evening. Homework number 3 is due a week from today, and exam number 2 is a few Fridays from now. What I want to do today is actually make some comments on homework number 3, maybe help you get through it a little bit more easily, and then I want to remind you about the connection of the eigenvalues of the system matrix A and how it relates to the transfer function. It actually is going to give you the same information as the poles of your transfer function, g of s, and we'll see hopefully that connection today. And then we'll start chapter 4, which is talking about feedback, and I will try to connect that by maybe making this, maybe I'm over generalizing, the transportation lecture. But we'll see where that comes in as we get to that chapter 4. Homework number 3, problem P324, is about solar collectors, and you don't even really need to know any of that, but I've provided that information. The one state is a deviation state. It's the temperature deviation from the desired equilibrium, and x sub 2 is the temperature of the storage material, which could be water. Maybe you're storing this solar heat in a water tank, or the temperature of the water. U sub 1 might be the conventional heat flow rate, which in this problem is set to 0. U sub 2 is the flow rate of the solar heat, and D is a solar disturbance, and you could think of that as clouds, something that changes the normal input to the system. The equations that you're given are 2 first-order differential equations, and if you look closely at those, you will see that the states do not couple each other together, meaning in the first one, on the right-hand side, the only state variable you have is x1, and on the second one, the only state variable you have is x sub 2. You do have inputs arising in both of those right-hand sides to change or to influence the time rate of change of x sub 1 and the time rate of change of x sub 2. And maybe what would give you a problem when you're trying to analyze this system is, what do I do with this disturbance? But the disturbance is similar to an input. And if you have u1 equal to 0, if we've now plugged that in on the x1 prime equation, we do not have anything. The only thing driving that system is the 1 due to the second input. And in x sub 2, we have the 1 from the second input and the 1 from the disturbance, which you see you could actually sort of collapse into just a 2 if you wanted to, driving the second set of equations. You could also put that in matrix form, and in this case, our input matrix now has 3 columns to account for the 2 inputs, u sub 1, u sub 2, and the disturbance d. And now I might ask you, what's the dynamic behavior or characteristics of this system? Or what I'm suggesting by that comment is, what are the eigenvalues of your system matrix? 3 and 2. It's a purely diagonal matrix, and your eigenvalues are then just immediately on the diagonal. In terms of dynamics, where are these eigenvalues located? And if we plotted those eigenvalues in the complex S-plane, where would they live? And the easy answer is at 2 and 3. But the deeper thinking answer is they're in the right half plane. That's plus 2 and plus 3. These will actually produce growing exponential responses. and you have then an e to the 2t and an e to the 3t. They are not coupled. You do not have any off-diagonal terms, and so you can now solve these individually if you want to, which is what I would choose to do if I were solving this. And it would fall out anyway if you performed that analysis. The decoupling would immediately come out. So you'll be able to hopefully minimize the time that you spend on trying to decode the information of this problem on homework number 3. The other problem that I want to point out is dealing with CP 3.4. We have a lot of different letters in front of our numbers, but this is now a computer problem. You'll need to use MATLAB to work it, and you should refer to sections 9 and 10 in Chapter 3, which essentially give you the MATLAB commands that are necessary to solve these MATLAB programs or these problems coming as computer problems, CP 3.4, and there's another computer problem which I don't remember the number, but you have 2 of those to work this homework set. Now let's get into our material for today, and as I said, what I wanted to do is start by talking about this connection between poles of the transfer function and the eigenvalues of the system matrix A. If I ask you to give me the general description of a system in state space form, could you simply recite that or write that down on a napkin or the back of an envelope? If I said, give me the dynamic behavior of a system, a generic system in state space form, what am I asking for? I'm sort of asking for cheer number 1, but I'm not wanting it yet in the cheer form, am I? I'm actually asking for A, B, C, and D. So I'm just asking you, give me A, B, C, and D in the state space representation form. Meaning, I'm saying, let's write it as the time rate of change of our vector, x, is equal to the system matrix A times x of t, plus the input matrix B, u of t, and y of t is equal to c x of t. And since Solomon's not here, we won't include the D matrix. How's that? But we could. We could say that this is plus D u of t. That's the general state space representation for a given system. We just need to know how do we populate the elements in those matrices, the system matrix A, the input matrix B, the output matrix C, and the direct feed-through matrix D. Now we could do cheer number 1 to give us the transfer function. If somebody gives us A, B, C, and D, what can we write down immediately for the expression for the transfer function? If we include the D, it's hanging out there by itself as the direct feed-through. Now, what I want to focus on is this SI minus A inverse piece. If we look at SI minus A inverse, which is a major part of that transfer function expression, that inverse is 1 over the determinant of that matrix times the adjoint matrix of SI minus A, which is the cofactor matrix transposed. But now if I said, can you now tell me which piece of that expression on the right-hand side of SI minus A inverse gives rise to the poles of G of S? We now know that the poles of G of S are the values of S that cause the denominator to vanish. So we're looking for an expression that's in the denominator, and that's this determinant Si minus A. So the roots of G of S are actually the roots, or the poles of G of S are the roots of the determinant of Si minus A. But if you've had a linear algebra class, that's screaming at you as something that you learned in linear algebra. Do you remember the definition of eigenvalues? Or one way to find eigenvalues. You might have seen that as the determinant of Si minus A, or the values of S that cause the determinant of Si minus A to equal 0, where I'm using these vertical lines to denote the determinant of that quantity, and this entire equation is now the characteristic equation. And for those of you that invested in a calculator that's either a TI-89 or the Inspire, it actually can compute this fairly quickly. You can simply implement the function EIG val, eigenvalue of, and you could put in as an example the matrix 3, 1, then in the second row it would be minus 2, 0, to produce the eigenvalues that you are interested in for that matrix, which are minus 1 and minus 2. Now, if you didn't buy the calculator, or if you don't have that, you can do it manually, which it isn't hard for a 2 by 2. Here's our matrix. And if we now look at lambda I, typically you see eigenvalues referred to as lambdas, so just view that as S if that's confusing. But now I have lambda I minus A equal to 0. Now that gives rise to lambda plus 3, 2, minus 1 lambda. We want to compute the determinant, and that's not hard. That's the product of the diagonals minus the product of the off diagonals. And we now see that we end up with this quadratic equation, lambda squared plus 3 lambda plus 2 equals 0. And that we can maybe see by inspection the factored form of that quadratic, or we now see that the two eigenvalues, the values of lambda, or the values of S that cause that expression to vanish, turn out to be lambda 1 equal minus 1 and lambda sub 2 equal minus 2, consistent with what we had found from our purchased form of finding the eigenvalues. But it actually gives you more insight, I think, to sort of step through that. For a 2 by 2, there's no need to even pull the calculator out of your backpack. So you can still get by with this 4-function calculator. Plus, minus, multiplication, and divide. That's all we need, right? Now, if you have the eigenvalues, what does that tell you about the way the system is going to shake or behave? If somebody gives you the eigenvalues, I want you now to start thinking about, oh, what does the dynamic system behavior look like as a function of time? If I excited this system with some initial conditions, what's going to happen? What's the natural behavior of this system going to be? What do the eigenvalues provide us with? They actually give us the modes of the system. And the modes are these eigenvalues in the exponent e to the minus 1t and e to the minus 2t. And if your eigenvalues are complex, then you have e to the minus the real part t if it was stable, plus j something, and that j something is your damped oscillation frequency. So knowing the eigenvalues, either real or complex, gives you a lot of insight into the dynamic behavior of your system. You know how quickly it collapses. Now you could say, which is the slowest mode in that system? Which one dies out the slowest? If you plotted these two and started both of them at 1, which one would disappear last? E to the minus t. E to the minus 2t is collapsing much more quickly, twice as fast, essentially. Or you could say, what are the time constants of these? So one is 1/2, and the other one is 1, isn't it? So now you could sort of think of these if they were decoupled in that way. You can also invoke cheer number 3. What was cheer number 3? For those that learned it for ID. That was our hunger one, wasn't it? That was phi of t, e to the at, right? So now that's e to the at. But if you know the eigenvalues, you now know a lot about this state transition matrix. You know the elements of that state transition matrix, phi of t, are in fact linear combinations of these modes, e to the t, or e to the minus t, and e to the minus 2t. Knowing the poles of the transfer function, or knowing the eigenvalues of your system, give you a lot of insight into the system's behavior. The big one is maybe, is it stable, is it unstable? All you need is one of those to be in the right half plane and your whole system is unstable. If they're stable, now you can start talking about how quickly are they dissipating, or how are they shaking if they have some imaginary part to them. How quickly do they move around, and how quickly do they decay? You now know a lot of information about dynamic systems and how they perform. What we haven't really talked too much about is we want to maybe change those dynamics. That's the whole point of this class, is understanding how can we manipulate the dynamic behavior of a system by introducing control. And the first thing that we'll talk about is feedback. Feedback provides us with a way to change these eigenvalues. If they're unstable, if we're not happy with them, how can we change those to be more like what we want? And that's what feedback is going to allow us to do. And that's in the next chapter, chapter 4 of the textbook. The classical diagram for a controlled system might have this feed-forward block described by G of S, a summing junction. Here's our output Y of S. Here is our input, let's say a reference input R of S. And then we actually take this output and measure it and feed it back, maybe with some kind of filter or some kind of processing in the feedback path, and compare that with the reference input. That's the reason for the minus sign. You're now comparing R with this filtered output, and many times in our class H will be 1. But we leave it in just for general purposes, and G may be more than just our plant. G might be the cereal or the cascade combination of the plant and the controller. But one piece that we will often be interested in is this air signal, E. And if I now am interested in that air signal, what is the transfer function between the reference input R of S and that air signal E of S? Is it just one? Well, it looks like E is R. Well, E is a little bit more than R, isn't it? Because of this feedback. So E, because of this feedback interconnected structure, is more than just R. And we want to know what's the transfer function between R and E. It's more interesting than just a 1. And we can do that with block diagram algebra. You could do it with Mason's gain. But now we are essentially saying treat E as the signal of interest, which a lot of times we've called our output, and R is our input, and find the transfer function between R and E. That's all we're doing. We're going to start trying to find transfer functions for many different signals in and around our system. And that means we may be interested in E relative to Y, E relative to R. Maybe we'll have a disturbance. Maybe we'll have a noise. All of those transfer functions we need to be able to obtain, and you now know how to do that. If we do algebra, E of S, the air signal is the reference minus, so we could say minus HY, but we know Y in terms of E, so let's just skip some of those steps. It's minus HGE. And that brings good things to life. Sorry. If you're not paying attention, maybe that's a dated commercial, but GE, have you heard of them bringing good things to life? That was the tail end of this. HGE. Sorry, that didn't go over very well, did it? My audience isn't into my punchline. But does everyone feel comfortable with that expression? And you see where that originates from the block diagram. And we can now, by combining, and typically since H and G are scalar transfer functions, they're not matrices, they can be interchanged, they commute. So it's just more natural to say GH than HG, just because I learned my alphabet and I can't say it backwards like some of you. So GH is easier for me to say than HG. Although I knew a guy, I used to work for a guy named HG, now I can kind of say HG. Anyway, those were his initials. Hobart, I better be quiet. So here we have 1 plus G of S, H of S, times E of S is equal to R of S. Or the transfer function, E of S, between the reference input R and the air signal E is now 1 over 1 plus G of S, H of S, times R of S. Which is the transfer function between the reference input, R of S, and the air signal. And is that the same as the transfer function between the reference input and the output? It's not cheer 2, is it? That's one of the reasons why it's nice to maybe remember these cheers. Recall that cheer 2 gave us y of s is equal to g over 1 plus gh times r of s. And now you can see the distinction between the transfer function between the reference input and the error and the reference input and the output. They differ not by very much. The denominator is still the same, isn't it? It's 1 plus gh, and that's what gives us the dynamic behavior. So the dynamic behavior of our system is going to be the same whether we're dealing with this transfer function between the reference and the output or the reference and the error. But the actual numerator in those two is different. One is g and one is just 1. So they are different transfer functions, and I want you to be clear that you can extract many different transfer functions from the same system interconnected structure. What are some properties or benefits to having this feedback? And the feedback is really giving us this denominator of 1 plus gh. Let's look or talk about now some feedback properties. One property of feedback is that it can reduce steady state error. And you're going, okay, that seems somewhat abstract. So let's put it into a context that maybe you're familiar with. How many people drive a vehicle? Or a bicycle? It's not really going to matter too much. So now you drive a car. Is there feedback when you're driving? Hopefully there is. There's several different inputs that you have to worry about. One is the steering. You need to make sure that your car, the center of your car, stays in the center of your lane. And if it starts to deviate, what do? You feed back, you correct. So you now move to the center of your lane. What about the speed? How many times do you have to change your set point? Maybe you need to go 25 miles an hour. So now you need to keep that speed around 25. Or now it changes to 45. Now you want to change it. So the driving, there's an error signal. The difference between your car's center line and the lane center line, that's an error, and you're trying to minimize that or reduce that, and you're using feedback to do that. There's also the difference between the desired speed and your actual speed, and you're trying to make that as small as possible. Maybe it's 25 miles per hour, and you're saying, let me try to get as close to that as possible. Hopefully you're not going 55 in a 25, because then you won't be in class. You'll be pulled over waiting for something to happen before you can get released to come to class. But driving now has these two inputs. Steering and speed that allow you to reduce steady state error. Is everybody comfortable now with feedback and reducing steady state error in just that very basic example? It also allows us feedback to improve or achieve stability. Here I was going to bring a broom in or a yardstick or something and try to balance it on my hand. Pardon? Yes, or a pickaxe. And it depends on the length, doesn't it? I think a broom is easier to stabilize, and this is an inverted pendulum, than a smaller, shorter object. And maybe a pickaxe, hopefully, was easy to control. If it wasn't, I wouldn't have wanted to be on the front row of that differential equations class. But here, you now want to balance a stick to make it stable, or How many actually rode a bike to class? That's like an inverted pendulum. You now need to make sure that you're upright or staying upright, and that you're improving stability with the feedback of your system. So feedback allows you to stabilize an unstable system or change the stability of a marginally stable or a system that you're not real happy with its stability characteristics. Another property of feedback is it allows you to reduce sensitivity. That's a big word, so we're going to dive into that a little bit, but one of the things, maybe I have trouble with sensitivity, but anyway, we're trying to reduce sensitivity. Maybe I'm not very sensitive, but here's another example. If you rode a bike to class today, did you ride it with or without a backpack? Pardon? With. Is that different than without a backpack? It is, depending on your backpack and how big it is. So what we're doing with feedback is you're actually able to accommodate that change in the system. So just hopping on your bike without a backpack, you have stability, but you also, because you're sensitive to now maybe having a backpack, you can still stabilize the system because of feedback. So the example here that I'm wanting to do is say that sensitivity is this notion of reducing the impact of a change in your system. You want feedback to overcome those changes in the system and still give you the same kind of behavior. So here, ride a bike with and without maybe a backpack. And you want to be able to stay upright whether your system is without a backpack or with a backpack. Now, what we want to do is talk about sensitivity in a more mathematical sense or an engineering sense. Sensitivity. Suppose, and this arises when we have system uncertainty, and that's the difference between you riding a bike with or without a backpack. There's the uncertainty in the system. Suppose that you have that uncertainty. Suppose there is uncertainty in system parameters. And what we're going to do, or system parameter values, what we're going to do in the lab number 2 is actually try to make the system behave the same, whether it's your system or your neighbor's system or someone else's system. We want the dynamics to look the same, whether you have spring 1 and 3 masses, spring 1 and 2 masses, etc. So those are the different parameters that are not the same in your system. So there's uncertainty in the system. Another case where you might have system uncertainty is in a motor. The motor or the winding resistance might change either as it's operating or with age. For instance, the winding resistance of an electric motor changes as the temperature of the motor rises as the motor is on for a while. And what you want is you want your behavior of that system, if it's controlling that motor, to be the same whether your motor's hot or whether it's cold. You want the system to be the same. A good control system should maintain we'll say satisfactory performance in the face of parameter uncertainties. Or parameter variations. And the way that we will try to accomplish that is by defining a sensitivity expression. So suppose that we now parameterize, suppose the system, let's say that's a plant that's described by a transfer function g of s, changes by some amount we'll call delta g of s. We want to know if our system changes by a delta g of s, how does the transfer function change? Or we're asking, what is delta t of s? And what we want to do is not just talk about an absolute delta t and a delta g. It's actually better to normalize those changes relative to the plant and the transfer function. So we are going to examine how this works on a relative basis, meaning we are interested in how does the transfer function change, delta t, normalized to the original transfer function relative to the change in your system normalized to the system itself. And this is our quantity of interest. But you know, after all of your calculus, that we don't really like talking about deltas as much as we like talking about differentials or small changes. And we want to now look at that quantity of interest in a differential setting. In a differential setting, that is when delta g now is this partial of g and delta t is this partial of t, this quantity of interest or this ratio is now called the sensitivity function. Or the sensitivity of the transfer function t of s to changes in the system or plant. And we have to introduce a notation for that. So the sensitivity of the transfer function relative to the plant is capital S superscript t subscript g. The sensitivity of the transfer function relative to the plant g. And we'll define that to be what we said it was. We now are interested in the partial of, partial of t over t over the partial of g over g. And maybe we multiply the denominator by 1, g over g, and the numerator by 1, t over t, and we end up with, bless you, g over t, partial of t with respect to g. And that's now our sensitivity of the transfer function t with respect to g. So we take the partial of our transfer function with respect to g, and we multiply that by our system g, or plant, and divided by the transfer function t. That will be our sensitivity of t with respect to g. And we can find another equivalent expression by going back to our calculus days, where we're now looking at the derivative of the natural log of f of x with respect to x. What is that? That's 1 over f df dx. So that now, if we did that here, we can now say thus, another equivalent expression for the sensitivity of t with respect to g we can find as the partial of the natural log of t over the partial of the natural log of g. And with equivalent expressions, sometimes it's more convenient to look at one versus the other. That's why we have these two different ways of expressing the same thing. We should end up with exactly the same answer using one or the other. Let's now look at a couple of examples of sensitivity to get a feel for how we might make these computations. And let's just look at comparing open loop transfer function, which maybe we'll describe as t sub 0 of s, 0 being for open loop, versus a closed loop transfer function, which we'll now denote as t sub c of s. And we want to see the sensitivity of an open loop system versus the sensitivity of a closed loop system, and see if there's any difference and why feedback might be helpful in reducing sensitivity. Let's start then with the open loop case. And that now is what we were calling t sub 0 of s. That has a pretty easy block diagram. There's our output y relative to the input r, and it's all just our open loop system, g of s. And in this case, then, our transfer function between the input r and the output y, we are calling t sub 0 of s, is g of s. No cheer necessary, right? Now, what we want to do is we want to compute the sensitivity of the open loop transfer function t sub 0 with respect to g. And that was described or defined as the partial of t naught over t naught over partial of g over g. That's the defining expression. And now we can pull out the g and the t naught so that the g comes upstairs and the t naught remains in the denominator. And we now need to find the partial of t naught with respect to g. Or what is this partial derivative? If I'm taking the partial of t naught, which is g, with respect to g, what's the result? It's just 1. So now this expression is simply 1. Well, maybe I'll show where that's coming from. If for those that are missing from today, maybe that they're just looking at the notes, they're going, where did that come from? Well, now t naught was just g, so we now have the partial of g with respect to g, and that's 1. So that our overall sensitivity of the open loop transfer function with respect to g is now g over t naught, which is g, times this guy, which was this piece, and g over g is 1. And so now the sensitivity of the open loop system with respect to changes in the system goes right through. So if you change g by delta g, you're going to change the transfer function by exactly the same amount. We haven't reduced anything in terms of sensitivity with respect to changes in our plant or in our system. Hopefully with the closed loop, that will be a little different. So if we look at the closed loop transfer function, we now have t sub c of s, and we know that block diagram. And because we know our cheer, we know the transfer function. T sub c of s is now g over 1 plus gh. That's simply cheer number 2. So that now if we want the sensitivity of the closed loop transfer function with respect to g, it's now the partial of t sub c over t sub c over partial of g over g, which is now g over t sub c partial of t sub c with respect to g. So now we want to calculate the partial of t sub c with respect to g. And that's just this g over 1 plus gh. We have now this quotient that we're trying to find the partial derivative of. And you can use your calculus if you want on that. What's the partial of g over 1 plus gh with respect to g? If you remember your calculus, you can do it from the formula. You now have the derivative of the numerator times the denominator. So let me say the denominator 1 plus gh. What's the partial of the numerator with respect to g? That's just 1 minus the numerator times the partial of 1 plus gh with respect to g. That's just h. All over the denominator squared. And if you do the simplification in the numerator, you now have that we have 1 over 1 plus gh squared as the partial of t sub c with respect to g. But that's not the sensitivity, is it? That's a piece of the sensitivity. The sensitivity is including g over t sub c times that partial of t sub c over partial of g. We have g, and what's t sub c? Cheer 2. That's g over 1 plus gh times 1 over 1 plus gh squared. So this guy eliminates one of those. The g's cancel. And what's the sensitivity then of our closed loop transfer function with respect to g? 1 over 1 plus gh. And now with feedback, if we make gh big, we can reduce the sensitivity of our closed loop transfer function with respect to the plant G. So if you have changes in your plant, they're not going to be modified or come through in your transfer function as large as what they were in the original system. And we'll pick up at that point on Wednesday.